Now let us understand one program for matrix addition and subtraction, and this we will use two-dimensional array for the purpose. Now you can see here, you all of you know the logic for matrix addition and subtraction, right? You will have a matrix like this and second matrix like this, and the result of addition is like this, right? And you can simply do this is as corresponding addition of corresponding elements, that is 2 plus 1, that would give you this 3, okay, and 7 plus 1, that will give you this addition, fine. This 4 plus 9 will give you this addition, and this 3 plus 3 will give you this addition. Okay, so it should, the logic should not be a problem for you, right? But the only thing that you have to see is how to access the particular elements together and to make the corresponding addition. Okay, so right now you know that every element of a matrix will be handled with the help of indexes, right? So for the purpose of addition and subtraction, it has to be compulsory that the row and column should be equal. Okay, so this you have to check. I have not given the condition for the for due to the lack of space over here, but you can check the condition whether addition and subtraction is possible or not in the given matrices. The row and column given are to be equal to each other, right? And we have taken some matrices, that is A, B, and C over here. So what is the A is your matrix number 1, B is your matrix number 2, and C is the matrix number 3, and this would also be our result matrix, right? Resultant matrix. Okay, what we require, we need to A plus B. Okay, what we require mathematically, we require C equals to A plus B. Okay, writing this is very simple in mathematics, but here you have to do it element by element, because plus operator always works on in C programming, it works on one element at a time or one integer at a time. Okay, so you cannot do A plus B and it will directly add all the corresponding integers. No, you have to do this, right? You have to add particular integer of the same indexes, particular integer of a from the same index. You can see there is ij and b is ij, so they both are corresponding to each other. So if I take it like this, 2, 4, 7 and 3, this is our example, and this is our 1, 9 and 1 and 3. So, do you know what is the index of this particular number? This is A 0 and 0, and here similarly it is B 0 and 0. So, what is required? This for getting this C 0 0. Okay, we require to add A00 plus B00. Fine. So to get C01, that is this is your C01 location. Sorry, this is your A01 location. For getting C01 location, this is your four locations. Okay, and this is 01 and this is 01. So this is your 00 location, this is your 01 location. For getting this 01 location, what you need to do, you need to have 01 A01, which is this number, and we require B01, which is this number. So these both will be added and it would be placed in C01. Okay, so this is the loop that from this we have done, that we have scanned I for all the rows. This is row major scanning because row is taken in the outer loop. So this is row major scanning, right? And you can see how we have printed, how we can print the matrix in a matrix form. There you can see I have used backslash tab to make a tab difference. Okay, backslash t for tab difference, and we have changed the line after every row. So the row finishes, every row finishes is this, and after every row we change line, right? So this is after row, this is one row. Fine, in one row we scan all the columns, right? For every row we scan all the columns through this. We scan all the columns through this, and this is used for different rows. In every end of the every row we change the line. So this is how we can print the elements in the matrix form, because we took it in the linear form and default it stores in in a row major form. So that is why we stored 2 here, 4 here, and then 7 and 3. So this was the row major storage. You stored like this first, and then you come to the next row. So this is row major scanning. And the second matrix is also printed like that only. You have a new line just after the just after every row, and result of addition can be estimated like this, as we are doing like that. Cij everywhere you can write that Cij generic, we can write that is it is equals to Aij plus Bij. Okay, so corresponding elements are added, or for subtraction it would be minus sign for us. So this line works for you, and as soon as you estimate Cij, you can also print it and put a backslash t for this result. Backslash t is there, and after you finishes complete row, after you finishes complete row, that is you complete column. Okay, one row and all columns, right? Once you finish all columns addition, then you shift to the new row by after printing backslash n. Okay, so this is how matrix addition and subtraction takes place. Now let us do some transpose of a matrix. Okay, here we will also take the matrix as input also, because this is what we also require. Okay, so this is the loop. For here we have only declared the matrix. We have not initialized it like we did here. This was the initialization of matrix what we performed. But here we have only declared the matrix of 3 cross 3. That is, there are 9 elements. Fine, 9 elements are there. 9 integers are there, and row and column are equal to each other. Okay, for transposing, you remember that it has to be a square matrix. So that is why the row and column to be same. So you can also make a check over here that if row is not equal to column, then you can print an error also, because it is not a square matrix that you can do by your own. Okay, so for I equals to 0, I is less than row and I plus plus. So what we are doing, we are taking input array, and what method we have followed is row major. And why row major? Because the outer loop is for row and the inner loop is for column. So it is for every row you store first all the columns. So this is the row major form. Okay, row major form of storage. So every time an element is entered by the user, okay, these are the elements suppose entered by the user, you can see that they are stored in row major form, right? You can see that they are stored in row major form. Fine. So these are stored in row major form. You entered one, two, three. So one is stored here, second, third. So first row, first row, second row, and third row, or we can say the row of the zero index, one index row, and two index row. And these are the zero index columns, one index column, and two index column, or I can say first column, second column, and third column. Okay, so for zero index row, you first filled all the rows, or for all the columns, right? So this is your row method. Okay, row major method. So this is the first, the input matrix is taken here. Now this input matrix is printed with the help of same syntax, that is Aij is printed, and we have printed it in the row major form. And every row, after every row, we have used a new line operator to change the row. Okay, now do you know the logic of this matrix transpose? This suppose I take a matrix, suppose I take the input matrix only 1, 2, 3, 4, 5, 6, and 7, 8, 9. Okay, this is how it is stored over here. And if I want to calculate its transpose, right? So mathematically, if I do this, this should be like that. Okay, 1, 2, 3, 4, 5, 6, and 7, 8, 9. That is all the except this diagonal, all the elements should get replaced by its corresponding shadow or corresponding reflection in the diagonal. This uh, diagonal separates it into upper diagonal, okay, upper triangular matrix, and this is your lower triangular matrix, right? And every element, corresponding element of upper triangle and lower triangle are interchange their positions, okay. So I can simply say that yeah, if I see the indexes carefully, 0 1 2, and I will also write 0 1 2. So I can say that whenever the indexes are equal for the diagonal, you can see that indexes are same. Okay, indexes row and column are same, right? So I equals to j. Fine for diagonals. Okay, because you can see that 0, 0 is 1, 1, 1 is 5, and 2, 2 is 9. Okay, so I equals to j. Whenever I equals to j, this is diagonal. So we don't have to interchange. No interchange is required in this condition. So this is the first condition that we need to understand to do the matrix transpose. Apart from that, apart from that, what happens that if this a, you can see that 4 and 2 are replaced, so index of 4 is 0, sorry, index of 4 is 1 0, and it is to be interchanged with a 0 1. Okay, and let us see one more interchange location, that is this 7 is interchanged with 3. Okay, so that the index is a 2 0 is interchanged with a 0 2. Okay, so can you see an analogy over here that a I j is interchanged with a j I. Okay, interchange. Okay, or we can say swap. This is the swap condition. Okay, and the for that particular where you not have to follow that where I equals to j, you don't need to swap. You only need to swap when I is not equal to j. But dramatically, you will see over here that if you start scanning like this, so you will not interchange this because here I is equals to j, that is 0 0, but you will do like this 0 1. So this particular index you will replace, this index is a01 and it would be interchanged with a10. Okay, so that should not be a problem, and this would be interchanged with this, so 7 would come here. Okay, 7 would come here and 3 would come here. Okay, and when you will come to 2 while scanning, so you scan this position, this position, this position, and then when you will come to this position, what will happen that this uh, 2 is index is a10, and if you take this also for the interchange, then what will happen, this 2 will again go to 4 location, right, and 4 will come here. So this would be a repetitive interchange of the same elements, right? So what is required, there has to be one more condition where you have to do either the upper triangular interchange or lower triangular interchange. Okay, because if you do both interchanges, then it would like suppose people goes from location A to B and a person comes from B to A. Okay, when the number, when you scanned A only. But when you go at the B location and then you will again ask them to interchange, so they will come back to their original location. Okay, so by this way, the interchange will not be possible, and you will get the original matrix back, right? So what you have to understand that aij and aji swap is only required to be done when I is not equal to j, and you have to also add a condition whether I is less than j or not. Okay, so either you can take I is less than j, or j is less than I. For any of the two condition, I is less than j would always be a matrix. Okay, would always be a matrix where I is less than j. I is less than j for this element and this element. Okay, for this element I is not less than j, and for this element I is less than j. Okay, so the interchange will happen for these elements only. For the where I is not less than j, their interchange will not happen. Okay, so if I write them in the form of indexes, then you will see it more easily. Okay, so I will write it like this: A00, A01, A02. Okay, this is 0. Sorry, this is 10. Okay, this is 20. This is 11. This is 21. This is 12, and this is 22. Okay, so for I equals to j, these will not be interchanged, and for I is less than j, where is I is less than j, we will only do interchange for this, and for this. So we have only chosen this will not do an interchange, this will not do an interchange, and this will not do an interchange. Okay. So for upper triangular, getting the upper triangular matrix, we use this condition to get I is less than j. In upper triangular matrix, the condition is that I is always less than j. Okay, so we take two conditions whenever I is not equal to j and I is less than j. Okay, so in that condition, we swap the elements and we get the transpose. The transpose matrix can be printed like this, as we have done the remaining matrices that can also be printed as usual. And this is the transpose matrix. You can see that 159 they have not changed. Okay, and only this 4 is exchanged. This 2 is exchanged with 4. So this is 4 2. Okay, their exchange happen. Okay, and this exchange happen, right, and this exchange happen. Fine, so these exchanged happens, and this was the process of matrix transpose. Okay, now I'm putting you some practice examples, so you have to do this practice for 9 and 10, that is we did these addition, subtraction, and transpose, and apart from them that you have to also do matrix multiplication. Okay, and addition of diagonal elements only. So for the diagonal elements, you have to check only the condition when I is equals to j. For all I equals to j, you just have to do sum equals to sum plus a I and j. Fine, and you have to initialize sum from 0. Okay, so this condition you can follow, and this is the method to do summation of all diagonal elements. Fine, for matrix multiplication, let me show you an example for matrix multiplication. I believe you all know that matrix multiplication require R1 cross C1, and it needs to be if multiplied by R2 cross C2. Okay, so the condition that is compulsory is C1 should be equals to R2. Okay, and the result of multiplication, that is M, the result of multiplication will be in the dimension of R1 and C2. Right, this is the compulsory conditions for matrix. So first you have to take input, as this input can be a, this input can be b, and the output can be c, and c has to be r1 cross c2, and you have to first check that c1 is equals to r2 or not. If it does not happen, then you can print an error. Right, this is the logic for matrix multiplication. You can see over here I have given you a program also for this particular thing. You can see that the column of the first matrix is equal to the row of the second matrix, so these two are same to each other. So it means the matrix multiplication and can happen, and you can see that the number of rows and number of columns in first and second matrix respectively is seen in the resultant matrix as row and column. Right, so you can see here here R1, R2, R3, we have taken. Okay, you can also take these elements from the user. I have taken for the sake of easiness to explain here. I have taken it initialization mode. Okay, now you can see I have also used one more element. Okay, do you remember how to? So let me explain you this particular example with the help of the indexes. That is the matrix is 2 4 7 and 3 5 2. This is your A matrix, and this will be crossed by B matrix. B matrix is simply 1 1 1 1 4. Okay, 1 1 1 4 and 9 3 5, right? And we want to get C matrix. Okay, C matrix, and it would be of size 2 cross 2. So there would be 4 elements. So take so if I take C 0 0, I want to estimate it. First, I would write it mathematically. Mathematically, what you do, you multiply this whole row from this column, right? What you do, you multiply whole row of first matrix to the whole column of second matrix and do a addition, right? So what you do, you multiply 2 by 1 plus 4 by 1, and this is 1 1, and this was 4. Okay, and then you multiply 7 by 4. Okay, so this multiplication you have to do. If I write it in the form of indexes, so that would be this would be a 0 0 to be multiplied by b 0 0 plus a 0 1 to be multiplied by b1 b1 0 and a 0 2 to be multiplied by b2 0. Okay, a relationship you might not have got from this. So I will write one more element for you, c01. Okay, so first I will write it like that. For getting this particular element, this is your 0 comma 1, or you can say first row and second column. Okay, so you will take this first row and you will multiply it with the second column. Okay, so you will simply do 2 multiply 9 plus 4 multiply 3 plus 7 multiply 5. This you will do for multiplication of first row and second column. Fine, first row and second column. Okay, so if I write it in the form of indexes, I will simply do. Okay, I will simply write a 0 0 multiply by b 0, sorry, b0, but 1 here. Okay, b0 first row and second column. Fine, plus a 0 1 to be multiplied by b uh, 1 and b1 and 1. Fine, and a 0 2 to be multiplied by b 2 and 1. Okay, so you can see here mapping these two, you can simply see that Cij, if I generalize it, Cij is equals to ai, and there is a number multiplied by b, there is a number, and there is j, because you can see that a index A's row is always same to C's row. A's row is always same to C's row, and here A is row and is always same to C's row. So what I have done, I am simply writing A and making a general formula, right? So I will simply write emptily, and then we will fill it with the formula. Okay, Fine. So what we have seen from the expressions that A's row is always same to the C's row, and C's row is I. Okay, so I will always write A's row as I. Okay, and you can also see that B's column is always same to the B's column is always same to the C's column, right? So B's column is always same to the C's column. Okay, so that you can see here B's column is always same to the C's column. So in the B's column I will write always J. Okay, and the remaining, that is A's column index and B's row index, you can see that it is in the incrementing fashion. For estimating this Cij, what we have seen that this index of row index of A is always same to the row index of uh, resultant matrix, and this column index of B matrix is always same to the column matrix of C matrix, right? Resultant matrix. So what we can do in the general formula, we can put rows of A is always I, and rows of J to be always rows of B to be, or columns of B to be always J. Now we can also see here that this column of first matrix and row of second matrix is always same, and it is also incrementing in nature, and this increment is up to the number of the rows, the number of the columns of the first matrix, or number of rows of the second matrix. So we can use this loop, we have to use this particular loop for making this addition possible. So this loop will start from 0 and go to R2. Okay, and R2 would be R2 is the number of rows, or we can also take this to be C1. Okay, we can use any of the two notations for this, because R2 and C1 are same to each other. R2 and C1, R2 and C1 are same to each other. Okay, so this is taken as K, so the K would be an increasing number, and it would be same for every pair, and it is increasing from 0 to R2 minus 1. Okay, 0 to R2 minus 1. Okay, so that would be Ci. Okay, and since it is an addition of incrementing K, so we will take Cij to be initially 0, that we do as sum equals to 0. Okay, initialize the sum, and for the sum we do this addition in iterative manner. Okay, this iteration with K equals to 0, K equals to 1, and K equals to 2. Okay, so this is K equals to 0, this would be your first. Okay, aik and bkj with k equals to 0, and then this would go in cij, which is initially 0, and then it would assign in cij, and in the next value of k, that is k equals to 1, for k equals to 1, again aik and bkj would be multiplied, and that would be added to the previous cij. This is was the cij. Now cij has summation of these two, and then this will be calculated and will be added to this summation. Okay, in this form the Cij final received is this, and this can be printed with the help of tab space in a row, and for when a row completed, a new line is used to change the row. This is how matrix multiplication is calculated. Okay, so we have seen some practice programs that you can do. You have to also do some practice on matrix finding inverse. Okay, so what you have to do, you have to take a matrix, or that would be an square matrix. Okay, that would be a square matrix. Okay, and you have to find out a inverse. Okay, so this is a very complicated problem to do with the matrix, but this is the this is the very important problem also, for the sake of making complete practice over two-dimensional array. Okay, and then you have to find the summation of elements of upper triangular matrix. Remember, the condition for upper triangular matrix is the index to be less than the row index to be less than j index for upper triangular matrix, as we have already seen in the previous session. And then j is less than I. Okay, j is less than I to be condition for lower triangular matrix, and we have done over here for upper triangular matrix and lower triangular matrix. We have I is less than j for upper triangular matrix and j is less than I for lower triangular matrix. Okay, so by this way you can do the summation of elements of upper triangular matrix. This is the practice program that you have to submit, right? Okay, so this completes our arrays of one dimensional, that is linear arrays, and two-dimensional arrays for matrices. Okay, you can do some other calculations for multi-dimensional arrays. The same way dimensions can be increased, although we it is very difficult to represent them physically, but mathematically that can be done for the logic purpose. Okay, in the upcoming lecture video we will do character arrays. We will do some programs on character arrays and strings, and then we will see the further topics of array. Okay, till then, stay safe. Thank you.